So I'm speaking about filtering the Grothendieck ring of varieties. And so first I'm going to talk about the Grothendieck ring of varieties. Then I'm going to talk a little bit about filtering and why the naive idea of filtering doesn't work. And then I'll talk about an approach that does work, more or less. So first, let's define the Grothendieck ring of varieties. The Grothendieck ring of varieties, and it's over a field K, but I'm never going to say K, I'm just going to write it. So it's written K0 of Vk is the free abelian group generated by varieties X. So we take all varieties, and those are the generators. And we quotient out by the following relation. For a closed immersion y into x, we're going to say that x is equal to y plus the complement of y in x. And when I say variety, I mean reduced separated scheme of finite type over K. And if you don't like that, it's what, a zero set of some polynomials intersect a non-zero set of some other polynomials. Okay, so we have this. It's a perfectly good object, except I haven't defined a ring structure yet. And on generators, the ring structure is defined by the Cartesian product of the generators. This is a commutative ring, and it's interesting because it's the universal additive invariant. By which I mean the following. Suppose you have a map of sets which goes from the set of varieties to an abelian group A, such that mu of x is equal to mu of y plus mu of the complement of y and x for a closed immersion. Then mu factors through K0, and you'll get a map of abelian groups here. Similarly, if in addition mu of x cross y is equal to mu of x times mu of y, then mu factors through K0 through the Grothendieck ring, and you get a homomorphism of rings. So additive invariants of varieties are, morally speaking, actually live on the Grothendieck ring of varieties. So if you want to study additive invariants, really you're trying to study the Grothendieck ring. A couple of examples of these. The first one is just point counting. So if K is finite, and L over K is also a finite extension, you can take mu of x to be the size of the L points on x. And it's pretty easy to check that it satisfies both of these relations. So we get a ring homomorphism K0 Vk to Z. And the second example I'm going to give is Hodge characteristic. The category of Hodge structures is an abelian category, so we can define a K0 group on abelian categories where this relation is going to come from short exact sequences. And then we're going to define mu, which is going to go from the set of varieties to K0 of Hodge structures, and is going to take a variety x to the alternating sum of Hodge structures on the cohomology with compact supports of x. And this is in the case when K equals C. And here, sorry, I should have written the complex points of x. So this is a manifold. You can take its cohomology with compact supports and it's going to have an induced Hodge structure from the manifold structure on X. And the reason that you get an additive invariant is that cohomology with compact supports is covariant on open embeddings and contravariant on closed embeddings. And so you get this long exact sequence relating the cohomology of X to the cohomologies of an open subset and its complement, and that gives you that this is a nicely well-defined invariant. And it's not very hard to show, but it takes a little bit of writing, and I don't want to go into it.
Are you assuming your varieties are non-singular?
No. Yeah, okay, well then you can actually reduce to non-singular varieties, and this works the same way. So might as well, but it'll also, so this will factor through K0 of varieties, but you're right, this takes a little bit more showing, but you can in fact reduce the generators of this to projective smooth the varieties, and then you have a slightly different relation, but it's not a big deal. Mostly I just wanted to write down an additive invariant and say this works. So this works. So invariants like this really study the Grothendieck ring of varieties, so it's a pretty interesting object in its own right, and that's what I want to study. It's actually quite surprising. There's not that much known about it. Right, so let's see what we can figure out just from basic principles in the definition. So first off, suppose that we have a nice isomorphism of varieties x to x prime. Well, this is a closed immersion, sort of trivially. So we have a relation that x prime is equal to x plus the empty set, because that's the complement of x and x prime. And then we say, OK, well, we also have this nice closed immersion of the empty set into the empty set, just by the identity. And we can write down the same relation again. We get that the empty set is equal to the empty set plus the empty set. So this had better be equal to 0. And then this is going to equal x. So in fact, any two isomorphic varieties are going to be equal in this ring automatically. So that's sort of a trivial example, but just as a warm-up. A slightly more complicated example involves actually cutting things up. So we're going to say that a piecewise isomorphism, is a morphism f from y to x such that for some finite partition of x into subvarieties, we have induced morphisms. So f is y into x. Each of these has an inclusion into x. So we have an induced morphism. So you take the restriction of f to the image of xi, and you want this to be an isomorphism for all I. And it doesn't give you the partition, it's just that there exists some partition such that this is true. So you've pulled x apart into pieces, and then you say each of these pieces of y is isomorphic to the given piece of x. So in this case, so an example of this is, so given this partition, we can take their disjoint union, and that inherits a map into x. And it's pretty easy to check that, in fact, this will just be the identity map for each of these. And so this is a piecewise isomorphism. And then we get the following interesting fact. So we get that x is equal to the sum I equals 1 to r of xi, because we said that it's a finite partition, so it's obtained by doing finitely many of these cutting out steps. So you're going to get this. But we have these isomorphisms, which means we get this. And it turns out that these are pieces of y, and this is a finite partition of y. So this is going to equal y. So in fact, we get that if there is a piecewise isomorphism from y to x, then x and y are the same in this Grothendieck ring of varieties. So following is an open question of Larson and Lutz from 03. Does the converse hold? So this means given x and y, which are varieties, such that x is equal to y in the Grothendieck ring of varieties, is x piecewise isomorphic? And what I mean by piecewise isomorphic is, does there exist a zigzag of piecewise isomorphisms from x to y? Because you don't necessarily have a single map, but you might have something in between zigzagging back and forth. This is unknown. This is known for low dimensions. If x and y are of dimension 2 or lower, then it's known. In some nice cases, for instance, if x contains only finitely many rational curves, it's known. And this is all from a paper of Liu and Sebag from 2010. But in general, this is not known. There's a couple of more cases that are proved in this, but pretty much other than the results of this paper, this is not known. So let's see. Well, we want to try to answer this question, or at least figure out something more about the Grothendieck ring of varieties that might point to an answer to this question. So here's something naive that we might want to do. And just as a hint, naive means it's not going to work. So if you see ahead of me why this isn't going to work, please don't say anything. We have this nice natural filtration on the set of varieties, which is given by dimension. So we might start reducing to sort of smaller subsets of this ring, which are generated by things of small dimension, and try to study them separately. So we can define K0 of Vk n to be the free abelian group generated by varieties with dimension less than or equal to n modulo the same relation. And the relation is nicely well defined, because if y immerses into x, then it's a dimension, at most dimension of x, so the relation is still well defined. So this is a perfectly well defined object. It's no longer a ring, but the product works nicely with the filtration in the way that you might hope. So at this point, everything is good. And then we think, OK, well, we have this nice chain of inclusions. And because every variety has a dimension, eventually we'll hit every element of this. So in fact, we converge to this. And we might want to just compute the associated gradient of this and then try to work backwards, trying to figure out what we can learn about the ring. And what are these cofibers? Well, that's pretty easy. An object in here, modulo something in here, is a variety of dimension at most 1, when we don't care about things of dimension 0, meaning points. So two things in here are the same exactly when they're birationally isomorphic, at least the irreducible ones. And so this is going to be Z, the cofiber, generated by the birational isomorphism classes in dimension 1. And similarly, this is going to be Z generated by the birational isomorphism classes of dimension 2, and so on and so forth. I'm actually going to come back to these sets later, so I'm going to call this S1. I'm going to call this S2, and so on and so forth. And so we get actually information about the Grothendieck ring varieties. It's free because its associated graded is free. Yay! Except that we have a problem, which is we don't actually know that these are injections. Why don't we know that they're injections? Well, it might be the case in some horrible universe that might be this one, that there's some variety of very large dimension W, and you have two varieties which are not piecewise isomorphic, which include into it such that their complements are isomorphic. I'm not even talking piecewise isomorphic. It's just isomorphic. This might be the case. And this means, so W is X plus the complement of X and W. It's also equal to Y plus the complement of Y in W. And these are the same. And so in the Grothendieck ring, these two things would be the same, even though they aren't piecewise isomorphic. And so we can't say that this relation is not induced by anything of lower dimension. It's only induced by this higher dimensional thing. So these things here, which we were so happy about, might not be injections. And in fact, I mean, dimension might not even really be well defined on this Grothendieck ring. I never even said that these had to be the same dimension. We can't just off the top of our heads, once we think of this horrible picture, we can't control the dimension of X and Y. But luckily, Liu and Sebag have done a bit of it for us. It turns out that dimension and Euler characteristic are good invariants on the Grothendieck ring of varieties. So if the class of X equals the class of Y in this Grothendieck ring, then the dimension of X equals the dimension of Y, and the Euler characteristic of X equals the Euler characteristic of Y. So, okay, so we do have a filtration by dimension, but we don't actually know what it is. We can't write down a formula for the nth level group because we don't know that these are injections. What we'd have to do is take their image in here and say, oh, it's that group. And then we can't compute the associated graded. And this whole picture falls apart because it pretty much says, well, if we know what things look like in here, then we know what things look like in here. But we don't know what things look like in here. We were trying to study from here to here. So this falls apart, and that's why it's naive. But maybe we can rescue this somehow. And that's what the rest of this talk is going to be about. It's going to be about rescuing this so that it will actually work and does not rely on knowing this. Because if we know this, then this works perfectly fine. But if we know this is a much harder thing than just wanting to know this part. So the goal of the rest of this talk will be to try to rescue this as much as possible and see what this kind of approach can give us. And yeah?
With complex numbers, can you say that more things have to be equal in X and Y?
Yes.
A lot of books say.
Say that again?
Well, thinking of various genera, various invariants of its recursive group study, for example.
Yes, I think so. I can't say off the top of my head, but I believe so. So what I'm going to do is, instead of looking at the algebra of what's going on here, which is what Liu and Sebag did, I'm going to look at the combinatorics instead. Instead of thinking, oh, these are varieties and they include and we have various algebraic formulas, I'm going to say we just have things, they include into other things. We can cut them apart by how they include. and see what information that can give us. So definition. An assembler is a Grothendieck site, and I'm going to explain what that is in a second. But in particular, it's a category satisfying three things. So first off, it has an initial object. Two, it has all pullbacks. And three, all morphisms are monomorphisms. Okay, so what does this mean? A Grothendieck site just means it has a bunch of information about which objects cover other objects. And this will be easier if I can write down an example. So I'm going to write down an example and then explain what kind of structure we have. So example. My objects are finite sets. My morphisms are injections. And the topology, which is the information that you need to have a Grothendieck site, is we're going to say that a bunch of morphisms, A sub I including into A. So A is fixed and AI varies over some indexing set I, is a covering family if, so I'll call this phi I, if the union of phi I of AI is equal to A. So what does this mean? And why is this an assembler? So first off, it has an initial object. This pretty much means it has an empty set in it, which includes into everything in a unique way. That clearly works in finite sets. M, all morphisms are monomorphisms, pretty much means that the morphisms are injections. This sort of gives us an ordering on which objects are bigger than other objects. Pullbacks just means we have intersections. So if you have A is a subset of C, B is a subset of C, we can take the intersection and that will also be a subset of C. And the topology says, well, which smaller objects contain all of the information of a larger object? Well, what we're saying is if we've hit every element of A from some AI, then it's a covering family. And then a quick definition. A covering family is disjoint. And we might not need this definition, but I'll just mention it. If these pullbacks, so you take two of these, and you take the pullback, and this is the empty set for all distinct I and J. So what this means is that instead of just covering all of A, we cover each element of A uniquely. So each element of A appears in exactly one AI, and we've hit them all. So a disjoint covering family is exactly a dissection of A into smaller sets. Okay, so that's sort of an easy example. I'll give two more slightly harder examples, and then I'll state a theorem about these. So another example. My objects are going to be polytopes in En, so n-dimensional Euclidean space. My morphisms from P to Q are going to be an isometries of En I'll call this phi, such that phi of p is a subset of Q. So it's just as though P sits inside Q in some way. And my topology is going to be the same. So these are, once again, these are, you have a large polytope and you decompose it into smaller polytopes. So a disjoint covering family is exactly going to be, you take a polytope and you dissect it into smaller polytopes. Right now it can be infinitely many or finitely many. I'm not worrying about that at the moment. And last example, this is the one we actually care about. I'm going to call it VK. My objects are going to be varieties over K. My morphisms are going to be compositions of open and closed immersions. And my topology is going to be generated by the following. So if we have a closed immersion y into x, then we take its complement. That gives a perfectly good open immersion into x. And it's generated by these. So pretty much we're going to say that a covering family is obtained by taking a variety, slicing out a subvariety, and get two other ones, doing it again, doing it again, doing it again, and you can do it as many times as you want. Okay, so this is what an assembler is. It's useful because of the following theorem. There exists a functor K from the category of assemblers, which I haven't defined yet because I haven't told you what morphisms of assemblers are, but I'm not going to worry about that at the moment, to the category of spectra. And this is actually the category of spectra. But if you don't know what a spectrum is, just think it's spaces, and you will not go terribly wrong. Such that A pi 0 of K of an assembler C is going to be the free abelian group generated by objects non-initial, objects of C, modulo the relation that for every finite disjoint covering family, A sub I going to A, so now I has to be finite, the sum of the AIs has to equal A. So this is, if you look at these are this is exactly what we want to get the, oh, I erased it, the Grothendieck ring of varieties when we apply this to VK. Because each of these gives us a covering family. It's finite and disjoint. So we're all happy with that. And we get exactly this relation, and those are the only relations we get. B pi 1 of K of C is generated by pairs of covering families which agree on objects. So the A's have to be the same. And the AIs have to be the same, but these morphisms, here we have phi i's and here we have psi i's, they can be different. So what this is you have an object A, you cut it up into some number of pieces, finite number of pieces, and you glue them back together to make A again. So what this tells you, this keeps track of more information than which objects can be cut up into the same pieces. This also keeps track of how we're doing it. And this is going to be an abelian group. So we're losing a bit of information because we have an abelian group, but this is giving us some information about how objects can be rearranged into themselves. So I'm going to talk about this a little bit in this very simple example over here, because there I can actually say what everything is. So these are very difficult to compute, because even though, in general, pi 1 is not very difficult to compute, especially given that it's abelian, that would just be compute homology, and homology is quite easy to compute. But
are there relations?
Yes, there are relations.
And you're not telling us?
Oh, I'm not telling you what they are, especially because I don't actually know that the set of relations I have is complete. There's a paper by Muro and Tonks which gives these kinds of relations, and they have an ugly set of relations which gives you everything but which you can't compute with, and a nice set of relations that it's not clear that it's the complete set. But I can definitely tell you that those are the generators. Okay. So let's look at this in this example of finite sets over here. So our objects are finite sets. So we have the free abelian group generated by all finite sets. But for every finite set, so given a finite set, set I, we have the following covering family. We have a single point set which will map to I in I for every I in I. So this is a finite covering family. It's pretty easy to check that it's disjoint because every point in I is hit exactly once. And so that relation over there tells us that I is equal to the size of I times a single point set. And we can assume that it's unique because we discussed before that two isomorphic things will be equal. And the exact same argument will work that worked with the Grothendieck ring. So the only invariant we have is the number of elements in I. And so pi 0 will be z. Right, so, right. And pi 1 is going to be z mod 2. And the reason for this turns out to be that, well, if we look over there, there's a bunch of relations, but some of them are the obvious ones. If you have a covering family, and then you take one of the pieces and you cut it up a bit more, then those are equal in the obvious manner. And so we can assume that all of our covering families in those generators break everything up into a point. So we have a finite set, we split it into a bunch of points, and then we have two ways of assembling the set from those. That's just a permutation of the set. So it's generated by the permutations of the set. And it's an abelian group. And the group of permutations has only two abelian quotients. Either it's z mod 2 or it's trivial. And you can play around with this and actually conclude that it's z mod 2, and this is going to be the sign of the permutation. And in fact, I could keep listing these because in this case, you can identify what the image of K is. And I can't tell you all of them because if I could, I would already have a tenured job somewhere because that's a major open problem in topology. But this does give a nice combinatorial interpretation of what pi 1 is. which is well known. But the
Even for finite sets, the spectrum is.
it's the sphere spectrum.
Oh.
And yeah, so for finite sets, it's the sphere spectrum. And so you can just keep going for however many homotopy groups of spheres are known. But one nice question to ask will be, well, can I give nice combinatorial interpretations of the higher homotopy groups of spheres? And it would be cool, but I don't know. OK. So that's what's going on here. Here, the pi zeros are the scissors congruence groups of En. If you're curious about these, so DuPont has a book called Scissors Congruence Group Homology and Characteristic Classes, which has a lot of cool computational results about these types of groups. But I'm not going to talk about them anymore today. So the whole point of defining these right now was to talk about the Grothendieck ring of varieties. And I very suggestively named that VK. So in fact, pi 0 of k of VK is in fact K0 of VK. So this is what we get is from this K theory functor is a space model of the Grothendieck ring of varieties. And you might ask, well, here we have a ring, and here we have a group. So really, when you say equals, you're lying slightly, because this is equal to the underlying group of this. And that's true, but actually we can say a bit more. The category of assemblers is symmetric monoidal. And ring objects, well, I shouldn't call them ring objects, I should call them monoid objects. Monoid objects map to E infinity ring spectra. And this it's not trivial. And I haven't even defined what the product of assemblers is. And I'm not going to. I'm just going to remark this means that K of VK is an E infinity ring spectrum. You define product in exactly the same way you do here, and then you mess around with assemblers to make it symmetric monoidal, and it works. So in fact, this is a ring. An E infinity ring spectrum is the space version of what a commutative ring should be if we're only dealing with things up to homotopy. And pi 0 of an E infinity ring spectrum is a ring. So this statement is actually true on the level of rings, not just abelian groups. And now, very nicely, we've gotten back to our naive approach. And well, it still doesn't work. But now we can say, OK, well, this didn't work after applying K0, which was applying K1, which is applying pi 0 of a space K. And so, but there are nice injections of spaces that are not injective once you apply pi 0. So it might be the case that what was going on is we had nice injections of spaces here, and then we applied pi 0 and destroyed all of that. So why don't we try studying that injection of spaces? So I'm going to define VKN to be the full subcategory of VK, with objects being the varieties of dimension less than or equal to n. and say, okay, well, really we want to rewrite this as now we have k of vk0 going into k of vk1 going into k of vk2 and so on and so forth, going up to k of vk. And we could say, okay, well, are these nice inclusions? I said, nice inclusions of spaces. And as spaces, yes, but now the fact that I'm working with spectra, not spaces, starts making things a little bit more complicated. And saying what nice inclusion means doesn't mean anything. I will tell you that they're nice enough, so I will draw them as nice inclusions. What nice enough means is that you can compute the homotopy cofiber of this map. And when I say homotopy cofiber, I mean, morally speaking, what the cofiber should be. And that will give you a spectral sequence which converges to the homotopy groups here. I'm going to leave these up because these will be relevant. So what we want to do is we want to compute the cofibers here. And then we'll get a spectral sequence which converges to the homotopy groups over here and will tell us something about it. Not sure exactly what yet, but it'll tell us something. So how do we compute these homotopy cofibers? Really, how do we compute anything at all with assemblers? So to say this, I'm going to say a little bit more about the category of assemblers. And to start with, I'm going to define the morphisms in the category of assemblers. So C to D is a morphism of assemblers. So first off, it is a functor. So on underlying categories, it's well defined. It preserves initial objects. It preserves pullbacks. And it takes covering families to covering families. And if you think about this, this is sort of the minimum you need for all of this to be well defined. To have a nice map of categories, it better be a functor, because otherwise it's just a map of sets. To preserve initial object and pullbacks is because we had a bunch of finite disjoint covering families in these definitions. And in order to take disjoint covering families to disjoint covering families, in fact, you need to preserve all three of these. The disjointness is defined through the pullbacks, and covering families are defined here. So this is just sort of the bare minimum you need to make this kind of thing well defined. And this is all you need. Now, if you look at the definitions of these pi zeros in some of these examples, for instance, polytopes in En, any polytope can be covered by simplices. So morally speaking, we should have been able to take the objects being simplices in En and define the same space. Now you can say, okay, but the intersection of two simplices is not necessarily a simplex, so that wouldn't have pullbacks, and that would be bad. But morally speaking, the same thing should have happened. Objects being finite sets should have worked equally well with taking all objects being just the singleton set. And then, because all of my discussion involved, oh, you cover everything by singletons, and you just think about singletons. And so really, morally speaking, finite sets should have been the same as just a single singleton, and polytopes should be the same as simplices. And in fact, it's true. we need the following condition. So theorem. If D going into C is an inclusion of assemblers, such that two things happen. First off, one, it is full. So really, D is just a full subcategory of C where the topology is defined in terms of the topology on C. And two, every object of C has a finite disjoint covering family A sub I going to A, such that A sub I is in D for all I. So every object of C can be covered by objects in D. Then K of D going into K of C is an inclusion. Sorry, obviously an inclusion is an equivalence. When by equivalence, I mean homotopy equivalence. So all of its homotopy groups will be isomorphic. It induces isomorphisms on all homotopy groups. In particular, pi 0 and pi 1. But OK, so for example, in fact, I can do examples on all three of these, which will be good. So for example, here, you can take the inclusion of the assembler, which just has two objects, initial object and terminal object, and map it into this one here, which takes terminal object goes to single point, so a singleton set. Then this functor satisfies that property, because every set can be covered by singletons. And so this induces an inclusion, an equivalence, and that's how you know you can actually analyze this by hand, the image of K of this by hand to get that this is the sphere spectrum. And so so you get that if you do finite sets, that's the same as doing singletons. Example here, which I quite like. Take the subcategory of where the objects are polytopes with diameter less than epsilon for some fixed epsilon. Everything can be cut up into very small pieces, and so this induces an equivalence. And this means that scissors congruence is a local property, not a global property. So for instance, you can actually do this in any nice enough manifold, like a geodesic manifold. And any two geodesic manifolds which are homogeneous and isometric locally will have the same scissors congruence spectra, which I think is kind of cool. And here, I'm going to do this on VKN. You can reduce it. You can take as the objects all varieties of dimension strictly less than n, and then just the irreducibles in dimension n. And every variety can be covered by irreducibles, and so you have to worry about intersections, but those are of lower dimensions, so they'll all be in there, and you can cut those out and cover them also. And so whenever we're worrying about things in dimension n, we can in fact only worry about the irreducible ones. We don't have to worry about anything else. And similarly, you can do smoothness in the same way. which is why I said earlier that, oh, it doesn't matter if we want to restrict to smooth or not. We don't even need to resolve singularities. We can just cut them out and pretend that they're a separate variety. Okay. But that still doesn't tell us how to compute those cofibers over there. That's just sort of told us, well, how do we do some of these computations? So let's compute a cofiber. Okay, so again, we have D including into C is a full inclusion of an assembler. So you need the following extra condition. If D satisfies the following, so given a morphism F in C such that B is in D, then A is also in D. So technically this said D is a sieve in C, but the idea is that somehow the objects in D are small, and anything that's smaller than a small object is also small. And so that's what this condition says. Then there exists an assembler C without D, which has as objects the objects of C without the objects of D. And then also we need to put the empty set back in, because everything had better have one. And then the morphisms are induced from C. And the topology, well, we're going to say that we have a covering family if it can be completed to a covering family in C by objects of D. So it was a covering family originally, and then we threw out a few pieces that were in D, and that's now a covering family in C without D. So if there exists a covering family of DJ, if there exists DJ to A such that, their union is a covering family in C. Oh, and I forgot to put the DJ as in D. And this gives a homotopy cofiber sequence on K. I'm not going to go into the details of what homotopy cofiber sequence means, but morally speaking, it means what we want to put there. Those objects are what we want to put there. So if these inclusions are of this type, then this is what should go here. And you might ask, well, we know what this map is induced by. What's this map induced by? And that's given there's an obvious projection morphism from C into C without D, which just takes every object which is in C but not in D to itself, and every object in D to the initial object. There's sort of And this condition just means, oh, it's well-defined. And that's what this map is given by. So now we just need to check that those inclusions of the filtered VKs satisfy this condition, which is pretty clear they do. If something includes into a variety of dimension n, n minus 1, then it has to have dimension at most n minus 1. So the inclusion of vkn into n minus 1 into vkn satisfies this condition. So now the question is, what is vkn without vkn minus 1? Well, as I said before, over here, we can reduce to irreducibles. And we can especially reduce to irreducibles because the intersection of two, if you have a reducible variety and you have an intersection of two, you look at its two irreducible pieces, say, if there's only two or more, if there are more, that's going to be something of dimension strictly less than n. So that's going to be in here where we're throwing it out. So now a variety literally is closed. It is covered by its two irreducible components. So first off, the objects are just varieties of dimension n. And so now we can just say from the approximation theorem, which is right up there. So by approximation, we can assume that they're smooth, although we won't actually need smooth and irreducible. But we still have a lot of different objects. If you have a variety and you have an open subset, that open subset is dense. And so all of our covering families have now turned into single element sets. So all finite disjoint covering families are singleton sets, which are just of the form, I shouldn't use x, U including into x, where this is an open immersion. This is where we need irreducibility, obviously. And, and the morphisms are just, isomorphisms or open immersions between varieties. But we'd really like to say more about that. This is starting to look like it has a lot to do with this, which is as it ought to be, and as we wanted it to be. But it's not there yet, because so we can do a second reduction. So now we can reduce to the following subcategory. We're going to look at objects in the following way. Pick a representative in Sn in each class in Sn. And I'll move to the next board, I'm sorry. Do not have enough space there. So pick a representative of each class in Sn and let, I was just calling it Wn, be all objects above a representative. So we're again reducing to a subcategory. And we've picked a representative in every birational isomorphism class. And we look at all of its subvarieties, including itself, obviously. And we look at that subcategory. We just care that there exists a map to the representative. We don't pick one. So we have this sort of full subcategory. And so approximation still applies. So k of Wn to k of Vn without Vn minus 1 is also an equivalence. But now we have, we know a lot about the structure of this. First off, we have sinks. So each of these representatives is a sink. There are only morphisms into it. There are no morphisms out of it. So the representatives are sinks. So there are morphisms into them, and there are no morphisms out of them. And in addition, every object maps to exactly one sink. And this is because if something maps to two of them, then those two are birationally isomorphic. Because it's an open subset, it includes it into each one. It's an open subset of each one. Woohoo, they're birationally isomorphic. So there's exactly once. So the category looks like this. You have initial object, you have these representatives, and then you have a bunch of things sitting here that map to here, and then a bunch of things sitting here, and a bunch of things sitting here. But they don't interact. It's just sort of a bouquet of categories all glued together at the initial object. And it's actually pretty easy to see, once you know the definition of K, which I still haven't told you, that what this does is means that this is a coproduct of these different categories. So if we let Wn sub x be the part above x, so for x one of these, k of Wn will be equivalent to a wedge over Sn of k Wnx. So now we just need to figure out what each of these is. And this is, you know, we've done a lot of sort of reduction and then reduction and reduction again. We've used this approximation theorem every time. But now you can no longer approximate in this way, because any subcategory of Wn above x is going to be morally equivalent to Wn of x. Just reducing to a smaller open subset isn't going to do you any good. So you need a separate approach. I was hoping that I could put it here, but unfortunately I can't, so I'm going to move over here. Is it? What time is it? Oh, I'm so sorry. I was checking, I was like, wow, that's a, I'm so sorry.
It's actually 7 minutes after 3 already.
Yeah, okay, fine. Then I was like, wow, I have so much time. Why do I have so much time?
Wondering about that too.
Yeah, I'm very sorry. I was. Thank you for pointing that out. Okay, well then. Yeah, it was perfectly fine at the beginning. Okay, so I sabotaged the clock with my telepathy. Yeah, so I'll just cut to the chase then. This is equivalent to the suspension spectrum of the classifying space of the automorphisms of the function field. So this is pi 0 of this. So these are, in fact, pi zeros of the spaces that go here. But they tell you something about the higher groups, too. And more importantly, it tells you something about what's going on. And I will take 1 minute to write down the spectral sequence. So you get a spectral sequence where this is going to converge to the Grothendieck ring of varieties. And this is going to converge to something else, pi 1. And this is going to be a sum of z's, one for every thing in, this is S0, x in S1, x in S2. And this is going to be a sum over also x in S0, x in S1, x in S2, of the automorphisms of k of x abelianized. Because you have to abelianize pi 1 to get these. And the differentials are going to go like this, and so on and so forth. They're always going down in this column, so this is going to converge nicely. And it turns out that the question of Larson and Luntz is equivalent to asking, are all of these differentials 0 or not? And they're mapping into a free group, so at least the lowest one that's going to be non-zero is mapping into free groups. So you
only the ones from the ones.
Yeah. Only the ones here have to be 0. So they map into free groups. So everything fine. I'm lying. There's also z mod 2s here, but they don't matter for what I'm about to say. Since they're mapping into free groups, they can only do it in a non-zero fashion if they're infinite. So for instance, if your variety is of general type, this group is finite, and so the differential is automatically 0. If your variety is projective space, then you're looking at the abelianization of the Cremona group, which is also going to be torsion, at least, and therefore it's always going to be 0. And you can find varieties where these are non-torsion groups, but so far all of the examples I've seen have also had all differentials be equal to 0. So an interesting question is, can there possibly be a variety where the differential is not 0? And I don't know, but I've been looking into that. And that was what I wanted to say. I apologize for going so far over.